Hello, ladies and gentlemen. We're going to talk about friction today. Okay, come on, you silly machine. There we go. Boy, it wants to, it's acting weird on me. Okay, friction, what is it? It's reality. And to understand real structures, real mechanics, we need to model it. So the mechanical model is that friction is due to small defects, microscopic scale, even atomic scale defects between two surfaces. And it's like a bumpy surface, you've got two bumpy surfaces and they're riding up over each other. And it takes a certain amount of force to get over this hill, a certain amount of force to get over this hill, and so on. And presuming there's no friction at each of these individual points, you still have to exert some lateral force to cause and you're going to have some resistance because you're going up an incline. It's pulling an incline. And they're microscopic, atomic scale. Okay, and it's amazing how well this model works, actually. So we model friction as being tangential to the surface. The this line of force, the normal force, might not intersect the center of mass. The okay, and that the frictional force is proportional to the normal force. So we have for static friction, for example, the force of friction is less than mu s, the coefficient of static friction, times the normal force. When the force of friction equals the coefficient of static friction times the normal force, then it's what's called on the verge of sliding, impending motion. And in this case, you have an angle. This theta angle is given by the inverse tangent of the coefficient of friction. Rs is the combination. When you add the frictional force and the normal force together, you get the reaction force, R. And it's amazing how well this model works. There are some deviations, chemical bonding, for example, so that the width of a tire increases the friction, but it's a small effect compared to this is the big one. This is how we model nearly all friction problems because it's a pretty darn accurate approximation. So I want to look at some typical static friction coefficients. Metal on ice, very low. Wood on wood, 0.3 to 0.4, 0.7, something like that. Lubricated steel on steel. So this has to do with trains. Trains are incredibly efficient, energy efficient, because they might look, oh my gosh, those things have a heck of a lot of resistance. But when you look at the total tonnage of what they haul, that they do better than semis, automobiles. Only ships at sea do better. So, uh, but the low coefficient of friction means you can only go up a hill that's so steep. You can't go up a hill that's very steep. Rubber, on the other hand, an automobile can go up a 45-degree incline, which is kind of amazing, but a train can't because of the coefficient of friction. It's got to do some special things to get up those very high mountains and things like that. They they literally build switchbacks for trains so that they can go up mountains, steep mountains. It's it's kind of amazing to think about. But also this low coefficient of friction is part of the reason why trains are so efficient. There's another reason, but we'll get to later in the chapter, as a matter of fact. Okay. Kinetic friction, you're already in motion. Same sort of model. It's kind of like a car going through a pothole. If you're in the pothole, it's hard to get out. If you're going over the pothole, it doesn't take as much energy to just to have some momentum and go through it. So here's a plot. Frictional force versus the load force. That frictional force is going to be proportional, 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 up to this is mu s n, this point at the top. And then it goes to mu k n. Mu k is generally less than mu s, and it's flat. And what happens out here at high forces, anybody's guess. Tell you that. So equilibrium, you have a problem like this, and you ask, can you solve it? Yes, just solve it. Go solve it. You have what is it? 6 equations, 6 unknowns, and you're presuming that you know the lengths and you know the angles. But at the very end, you need to check. Make sure that this force here is less than mu A NA, and that this force is less than mu C NC. So you calculate how much these forces are, and if they're less than that, you're in equilibrium. You're fine. Now here's another situation. This time we want to find impending slip when this thing starts slipping, a ladder against a wall. And we need the two friction equations. Okay. Let's see, did I? So, yes, if something's in motion, now I've been using static friction so far a lot. Realize if an object's in motion, we use kinetic friction, the coefficient of kinetic friction. And if we're looking at equilibrium, if an object is not moving, we use the coefficient of static friction. So from now on, I might just use mu to represent friction. And you guys have got to figure out, is it in motion or is it not in motion? Okay, come on, move on. Impending motion at one point, for example, point A. Then you have 7 equations. You have, let's see, 1, 2, 3, 4, 5, 6. 7 unknowns, and you have 6 equations plus the 1 friction equation. 7 equations, 7 unknowns. So here's an example: a refrigerator tipping. This is where you've got impending motion at one point. So you model it as frictional force is acting at point B, normal force is acting at point B. That what is this H? So that it's impending. So this refrigerator is impending between slipping, it's not going to tip over, and tipping over. If you put force higher than H, the refrigerator will tip over. If you put force lower than H, refrigerator won't tip over. So this is a typical kind of problem. And let's go to a specific problem then. Let's take a look at something specific. So we got this kind of situation, force of 80 newtons applied at 30 degrees, and ask, is it going to remain in equilibrium? And it's a 20 kilogram crate. So we have 196.2 newtons acting down, and that would be the normal force acting up then. I take that back. You also have this force at an angle acting down. So you actually have to add 40 newtons to it. So here's 40, 80 sine 30 is 40. 196.2, 236.2 has to equal NC. And then um, the force of the force of friction, 80 cosine 30, force of friction is equal and opposite. Is the force of friction less than zero point 0.3 times, let's see, coefficient of friction was 0.3, yeah, 0.3 times that 236.2. And there's the moment equation too, which I think would be redundant, would it not? Okay. So NC is this, F is this. Is it less than, is this less than uh, mu S NC? Well, here's mu S NC right down here, and it is. So it won't slip. Okay. So a bunch of vending machines, dump truck raised to an angle of 25 degrees. The vending machines begin to slide off the bed. So we'll get to this problem next. Good time to stop this video and go to the next one.